Here are the solutions to homework set number 7 for ECE 476. In this homework set, we're trying to measure the thermal time constant of a coffee cup. So starting out, I've got a DSB80 temperature sensor. I've got it connected to a Pico, and it's displaying the temperature in Celsius. With that, I can measure, in this case, the room temperature. I'm currently at 24.47 degrees Celsius. Measure the temperature of a cold cup of water. You put it in there, it cools down, you have to wait a little bit. What I'm seeing right now is the thermal time constant of the sensor itself. Eventually it'll settle out. That's the temperature of the cold cup of water. Or a hot cup of water is actually just a tin can. That's kind of the first step. I need to be able to measure temperature. So that's problem number 1. Come up with a way to measure temperature. So what I have is a DS18B20 temperature sensor connected between 3.3 volts and ground. The sensor's reading on pin 0 on the Pi Pico. The code to read that is straight from Bison Academy. I'm going to import one wire DS1820, identify what sensors are on the bus, starting at temperature conversion, wait 750 milliseconds to a temperature read, then display it. In addition to displaying it on the screen, I'm displaying it on the LCD display, which is what you're seeing right here. Now with that, I can measure a couple things like ice water, cold water from the tap, hot water from the tap, room temperature, whatever you want to measure. That's problem number 1. Problem 2. Now write a program that records temperature for 1 minute and then displays the answer. So this is what that looks like. As I run the program, it'll start logging temperature for some amount of time, I think 200 seconds. At the end, it'll plot. And this is what the code looks like. Same code we had before, but now I've got a timer interrupt set for 1 second. Every second, I take a reading. Back in the main loop, I wait for the flag to get set, which is once a second. Once you get a reading, I will do a temperature conversion, print it to the display. So this is, the first column is seconds, second column is temperature in degrees Celsius, and this is the hot cup of water that I'm measuring. Also display on the LCD the current time, the current temperature. That's what you're seeing right here. And record the data. At the end of 200 seconds, it'll plot it. And here's what the plot looks like. There's the temperature decaying. Axes aren't labeled, but just because I haven't figured out how to do that on the LCD display yet. But I can plot the data. So there's my temperature cooling off. This didn't actually work out quite the way I intended. Turns out temperature is actually got a very long time constant. In 120 seconds, it doesn't change all that much. What we're seeing here are bit levels. Problem number 3 says, okay, collect some data. Take that data, analyze it in MATLAB. So what I can do in MATLAB, I can take the data, copy it into MATLAB, say data is start of message, or start of data, paste, end of data. Pull off the first column is temperature, second column is degrees Celsius, calling it T. Ambient temperature I measured is 20.65. So the curve fit is the log of temperature minus T ambient should be linear in time. My basis then is just T and 1. Doing a least squares curve fit, here is the log, this is A, or minus A. This is log of B. So plotting the two together to make sure my data is okay, if I plot time versus temperature, time versus curve fit, so B is e to the second term, A is just A, plus T ambient. The raw data is blue, the curve fit is red. Okay, that looks pretty good. That's in MATLAB. Now let's do the same thing with the Pi Pico. So switching over to problem 4, what this program does is same as before, but I do a least squares curve fit using recursive least squares. So my initial value of my basis function is zeros. Initial value for Y matrix is 0. For 201 data points, I sample every second. I'll then add to the basis function x squared, x, and 1. Add to the Y matrix x times y, y. As long as I'm past the third data point, I'll then do a least squares curve fit, basically make sure that b is invertible. Then my time constant is just minus 1 over the first term. So what's being displayed right here is time in seconds, the temperature, the time constant A, what am I printing? Where? A and B. Yep, that's my time constant in seconds. And B, the temperature above room temperature that my hot cup of water is. That goes to a file, and it also goes to the LCD display. So here's what the LCD is looking like. So this is showing in real time the temperature of the cup, temperature of the room that just hard-coded. This is after 86 samples or 86 seconds. This is my time constant, 1642 seconds, and the temperature above ambient when I started. With that, I can start collecting some data. So let's find the thermal time constant for this highly collectible tin can. I took 3 different measurements. After 200 seconds, I got 3 numbers, 1823 seconds, 1580, 1680 seconds. From that data, I can find the mean standard deviation. So here's the mean, there's the standard deviation. I want to know what is the actual time constant for that coffee cup. Well, it is a number. The more data I get, the more certain I am of what that number is. So in this case, that's a population question. The sample size matters. So here my sample size is 3, so the standard deviation drops as the square root of sample size. So going 2.92 standard deviations left and right, because again sample size is 3, I know that the thermal time constant for this metal can is somewhere between 760 and 2210 seconds. Now that's a pretty big spread. That just means that my procedure for collecting data was somewhat wanting. To get better data, to narrow this down, I need a better design of experiment. But that's what I got for homework set number 7. So homework 7 for ECE 476, how good is my coffee cup? In this case, it's not really good.